How's it going? We got 59 PA4s turned in. That's awesome. A few people are still working on it. So questions?
What was the common error that you saw in PA4 in previous years and stuff like that?
What was the what?
Common errors that you saw.
So biggest problem with PA4 is usually the delete function followed by the breadth first traversal, right? And if you didn't get either or both of those to work, or you had bugs in there or something like that, don't panic, right? Those are hard things to code. And the experience you're getting in trying to get those to work and in debugging and all stuff like that, that's the real value in this assignment. Okay, getting something that, you know, perfectly deletes every single edge case, never segs faults. That's kind of nice, and it gets you a few more points, but the real benefit is, you know, just getting some hands-on practice working with these things, getting better with GDB or however you're debugging your code and so on. So this is definitely the hardest assignment in this course. It's probably harder than anything we actually do in 223 in some ways. So don't you know, beat yourself up if you didn't get it working perfectly. Turn in what you have. But yeah, so delete is tricky just because there's edge cases and you gotta have everything just right. If you have one place where you meant right and you say left, or you meant previous and you say current, right, all heck can break loose. You get infinite loops, you get seg faults, all kinds of things can go wrong. And it's kind of hard to debug, right? It really sort of pushes your debugging skills because you've got to be able to visualize what's supposed to be going on and then coordinate that with what actually your code says it should do, and then coordinate that with what GDB tells you is actually happening and sort of reconcile those. So that's tricky. The breadth first traversal, the algorithm is simple, but the details are fairly complex, right? Because you need a queue of tree node pointers, and you've got to be able to tell when your queue is empty. And if any of that is off just a little bit, then your BFS, you know, loses half your tree or something like that. Those are probably the main things. I've tried to really stress how I want you to delete largest node from the left, so hopefully that won't be an issue. But in the past, lots of people go online, they look at Stack Overflow, and they find some other way to delete nodes, and they code that up. And it's not what I'm looking for. So I don't think that's going to happen in this class. But that's been a common issue in the past. How do you feel about trees in general?
Powerful. Concerns.
They are powerful. Concerned?
Concerned smile. Like
Okay, good. That's fair.
I think instead of doing binary tree, we can make it multi-dimensional.
Yeah, you can have like 3-way trees, you can have a 26-way tree, which is what our try was.
How do you feel about, which do you feel is better, arrays or tree style more so?
Arrays are simpler and they're a little more memory efficient, but they're pretty limited in what you can do efficiently with them. But if you're not totally worried about efficiency, arrays are a good go-to for just storing some stuff and retrieving it. Yeah?
So in the traversal function, when we're printing out the numbers, you said you had to have a comma between them.
Mm-hmm.
Is it okay if there's a comma after the last one?
Yeah, I won't ding you too many points.
Like we'll ding them.
50, 60 max, you know. I'll probably take off a point if there's a dangling comma there, just because if someone figures out how to get rid of it, they should get a point for that. The easy way to get rid of it is to just use a global flag. So when you first call your traverse, right before you call your traverse, set a flag to 1. And then in your traverse function, every time you're about to print, see if that flag is set. And if it is, don't print a comma. If it's not set, print a comma. And clear the flag the first time you print. That's just kind of a standard trick. All right, so I opened up the remaining quizzes for you. So you got something to do for the next week. So quizzes 5, 6, and 7, I marked them as due March 8th. 5 questions each. Should not take you a long time. But one of them is on tries, one of them is on trees, and the other is on heaps. so just a chance to sort of rehash what you already know. But do them this weekend or something. So if there's any weird issues in there, let me know. But they should be straightforward. All right, well, we're down to PA5 then. So PA5 is our last programming assignment. We may have some ODPs next week, but PA5 is our last big programming assignment. Big thing to know is PA5 is due on Monday, March 11th, not Friday. So it's not 2 weeks from now. It's the Monday after this coming Monday. So you've got like 11 days instead of 14, or 10 days instead of 14. The reason being that you're going to present your PA5 to the class. And I need at least one person from each group to do a presentation in class. Okay, that's worth part of your grade. So if you're working alone, you got to come in and present. If you're in a group, at least one person has to present, but ideally everybody comes up. And PA5, I'm going to let you work in groups of up to 4 people each. Okay, the reason we do group projects is because when you're in the workforce, you're usually working in a team, right? It's fairly rare, unless you're at a really small startup or something, it's fairly rare that you're just totally working on a piece of code all by yourself. And it's totally up to you, start to finish, this is my product, right? Chances are, especially larger companies, you're working on a piece of a system. And somebody else is working on another piece, and there may be 50 people working on different pieces, and there may be 10 people who are working on integrating those pieces together, and there may be a team of people who are going to be testing this code as it gets developed and put together. And there may be a group of people who are documenting it, and it's a team effort, right? And that's kind of how a lot of this stuff works in academia, but especially outside of academia. So I really want you to sort of use this as an opportunity to continue this idea of how do we work in groups, how do we do team development. And there's a lot of ways to do this, and there's a lot of theory on how to do this, and a lot of this theory changes over time, and sometimes you look back and it's like, well, that was really dumb the way that we were doing this in the 80s, you know. But there's no one size fits all best answer to how team programming, team development works. But I want you to try to figure this out yourselves. So if you're working in a group of 4 people, spend some time thinking about what's a reasonable way to break this project into pieces in such a way that we can put the pieces together and get, a complete PA5 at the end. And sometimes, 3 people are working and there's a 4th person and they've been asleep for a week and a half and they're like, I need a group to work with. Can I work with your group? And you like this person, so you say, yeah, you can join our group and you can, add the comments to the code or something. That works, okay, but try to be a little more kind of deliberate about it, right? Up front, before you start coding, think about how can we split this into pieces. What are the easy parts? What are the hard parts, right? And maybe the hard parts we want to have 2 people looking at, or maybe we all want to do some brainstorming up front. But give some thought to that, and this is part of what I want you to talk about in the presentation that last week, is I want you to describe to the class what your team was, right? Who was in the team? How did you split things up? How did you put things together after they were split up? How well did that work? Did you have to make adjustments, et cetera, et cetera? So it's not just about, here's my code, I'm done, right? You're hoping to get something else out of this also. So that's the reason for the team aspect. Okay, so before I pull up the details of PA5, let's talk a little more about this knapsack problem. And let's look at some examples. So knapsack problem, you basically have an inventory, which is a description of all the items you can choose to put in your bag, how much they weigh, how much they're worth. Okay, so I've got some sample code. So So here's some sample code for an inventory. So so we have a pencil which weighs 1 pound. So we have a weight, we have a value, and we have an item. So we have this massive 1 pound pencil which is worth $10. And we have the doubly massive pen which is worth $21. And we have the 5 pound book which is worth $56.
Seems like for college.
And we have the 7 pound car which is worth $78. So this is the collection of items you have to choose from to fill up your bag, which has, whatever capacity it is. So let's just say your capacity equals 10. So you can put 10 pounds worth of stuff in here. So what items and how many of each item should we put in this bag to maximize the value? So what do you think?
We can organize by value per weight.
Okay, let's look at value per weight. So let me call this, let's just make so pencil, pen, book, car. All right. So weight of 1, value of 10, that's got a value per weight of 10. Value of 21, weight of 2, that's 10.5. 56 and 5, that's 11.2, and 78 and 7 is, I think, 10.14.
Might be 11.
11.14. So slightly less than the book. 56 over 5. 11.2, 21 over 2, 10.5. All right, so there's our value per weight chart. So the book's the most valuable item, right? And it weighs 5 pounds, so what do you think? Put in 2 books?
2 books would be the highest value you can get.
2 books would be the highest value you can get, because that's the most valuable item. If we put that in, that takes up our full capacity. So that seems like a good solution. So 2 books. All right, let's see what we get here. So 10 pounds, what does it say? Put in 2 books, highest possible value is 112. All right, so my code agrees with our assessment. All right, so what about if the capacity is 9?
We would still put in 1 book because 5 pounds can fit in that.
Mm-hmm.
Because it's the highest rated weight thing.
Okay.
We have 4 left, so the next highest one we could look at would be car, but that's too much weight there. So then we go down to pen, and we put in pen twice.
Okay, so 2 pens. 21. That's going to get us $87. Does that look good?
Maybe better to get a car and 1 pen.
Yeah.
Might be better to get a car and 1 pen. Because a car is 78 and a pen is 21. There's $99. Oh, I messed up the pen. This is 42. So that comes out at $98. So yeah, with a capacity of 9.
Wait, but isn't a car 7 and a book 5? So that's overflowing 9.
But if you get a car and you get a pen, that's 7 and 2 is 9.
Okay.
Right?
Yeah, my bad.
And so the code should tell you 1 car, 1 pen gets you a value of 99. That's actually better than starting off with the most valuable one. So this is what's tricky about the knapsack problem. So if you're allowed to take fractional amounts of things, right, we would take as many books as we possibly could, right? We would take 1.8 books, and that would fill up our bag completely, and we'd have the maximum value. And if you're doing, the whole food store where everything's in a bulk bin, you can take exactly as much of each thing as you want, or the precious metal dust store where you can buy 2.3 ounces of gold powder, right? Then this works great. This is an example of what's called a greedy algorithm. A greedy algorithm is an algorithm that you can solve efficiently by just trying to do the best solution possible at each point. So what's the greedy approach to filling this bag? Oh, this is like really valuable. Let's put as many books in as we can, right? And then we can't put in any more books. Well, this is the next valuable one. Let's put as many cars in as we can, right? And some problems, that will get you an optimal solution. Okay, that's a greedy algorithm. With the knapsack problem, greedy algorithm does not work. And that's part of what makes it so tricky to solve. So remember, this is the integer knapsack, and it's unbounded. So we don't have any restrictions, like there's only 2 pens available. We have an infinite number of each of these things, but you have to take a whole number of them. So we can't always just go by value weight. But nonetheless, we can solve this thing very efficiently by thinking of it in terms of solving subproblems. All right, so here's our algorithm. So cap is the total capacity of the bag. So 9 pounds, 20 pounds, whatever. And if we have an inventory, we can think of some arrays. So weight, bracket I, and value, bracket I. This is for the ith item. So we have some arrays that store this inventory information for us. And we want to write a function which I'm going to call maxval. And maxval takes a capacity and it returns the maximum value that we can store in a bag with that capacity. So let's think of these inventories as evil globals, but you'd probably pass them to your function. So we're going to write a function maxval. If I give it 9, it should return 99, saying that's the maximum value you can get. If I give it 10, it should return 112, because that's the maximum value you can get. Okay, so how do we do this? We could do this exhaustively. We could take, up to 20 pencils, 10 pens, 4 books, 2 cars if we have a capacity of 20. That's still a finite number of combinations, but it's a pretty big number. It's a few hundred possibilities to try. So here's the algorithm we're going to use. So whatever our best solution is, we're looking for the best solution here. Whatever our best solution is, it's going to contain at least 1 pencil or 1 pen or 1 book or 1 car. Agreed? Because our best solution is not an empty bag. So it's got to contain at least one of some item. Okay, so let's look at 4 cases. So case 1, let me call it case 0. Best solution includes item 0. So we'll think of this as item 0, 1, 2, and 3. So case 0, our best solution includes at least one of item 0. Well, what's the maximum value we can get out of a bag with this capacity if we require that our solution includes at least one copy of item 0? It's going to be the value of one copy of item 0 added to whatever the maximum value is we can get out of a bag whose capacity has been diminished by the weight of item 0. So this expression here represents the most we can get out of a bag if we put one copy of item 0 in it at least. Because when we put one copy of item 0 in, we're going to have this much value from that item, and it's going to leave us with this much capacity in the bag, and max val of this tells us the most value we can get out of that remaining capacity. Is that making sense? So if capacity is 9 and I start by putting a pencil in, the most I can get out of my bag is $10 plus whatever the most is that I can get out of a bag that holds 8 pounds. So let me call this C0. But it's possible our best solution does not include any item zeros. Right? But it's possible that it includes item 1. So best solution includes item 1. And in that case, the value that we get is the value of item 1 plus max val of the capacity diminished by the weight of item 1. And C2 is the same thing, and C3 is the same thing. And since we know our solution is going to either include at least one of items 0, 1, 2, or 3, the max value we can get out of our bag is going to be either C0, C1, C2, or C3. So max val of cap is either C0, C1, C2, or C3. Which one is it? Whichever one's largest. So return the largest of these values.
Largest of is also another thing we might have to write up.
Yeah. And how do we find the largest of these? Well, your best bet is while you're calculating these, each time you come up with a new potential largest, compare it to the largest you've seen so far. Just keep track of what the largest is so that when you're done calculating all of these, you already know what the largest calculated value is, rather than storing them in variables and making some function that takes a bunch of arguments. Just do it like you find the largest of a bunch of numbers a user types in. Just keep track of the largest at each point, compare each new number to the largest so far. So max val is really just a big for loop, right? For I equals 0 to the last item number, calculate the value of item I plus max val of your capacity minus the weight of item I. If that's bigger than the biggest value you've seen so far, record that biggest value. And when you come out of your while loop, whatever that biggest value is, that's the maximum value. And if we draw this out as a tree, so let's go back to our original inventory. So let's find max val of 10. Well, if we start with a pencil, then our maximum value is going to be 10 plus max val of 9. If we start with a pen, our max val is going to be 21 plus max val of 8. If we start with a book, our maximum value is going to be 56 plus max val of 5. And if we start with a car, our maximum value is 78 plus max val of 3. Does that make sense to everybody? Right, car weighs 7 pounds, our capacity is 10, so we've got 3 pounds left over after we add the car. And max val of 3, for example, we could put in a pencil and have 2 pounds left over. Or we could put in a pen and have 1 pound left over. And max val of 2, we could put in a pencil and have 1 pound left over. Or we could put in a pen and have no pounds left over. And max val of 1, we can put in a pencil and have nothing left over. And if you're not careful, you might also say, oh, but I could also do the value of a pen plus whatever I can put in a bag that holds -1 pounds, right? And that's not physically meaningful. So when we're doing this loop, you need to be making sure that this is not negative. If this is negative, what does it mean? It means we can't fit this item into our bag. The weight of that item is bigger than the capacity of our bag. So when you're doing this, you also need to test and make sure that this argument to max val is not negative. If it is, don't calculate this and compare it to your largest. But if max val has a 0, we're safe in saying that's just equal to 0, because that's the maximum value in a bag that can't hold anything. So don't do negatives, but for 0 we can just return. So that's how we get out of our recursion. If cap equals 0, return 0. So this, you could fill this out and you get a big long tree just like we saw with Fibonacci numbers. And we're going to be calculating some values over and over and over again. And this will really quickly blow up, even for small inventories. So we want to do this pruning. We want to use dynamic programming. We want to save these max vals every time we calculate them the first time, so that the next time we need max val 9, we don't go through all of the tree. We just pull it out of an array. And if this was part of, solving the problem for a bag that holds 20 pounds, and somewhere along the way we needed to know how much we can get out of a 10-pound capacity, we're only going to do this calculation once, and then we're going to save the value. And we'll pull it out again next time. So that's the basic setup for knapsack problem solution. And I want you to think about the algorithm. Don't think about the code yet. Okay. Think about what are we doing. We're breaking it down into sub-problems. Right? You have to put in some item, and depending on which item you put in, you get a certain value, and you get a modified capacity. And we're going to call our max val recursively to solve the capacity problem for these smaller values. And once we know, these 4 values, whichever one is largest, that's the value of max val 10. So part of your team effort may be, sitting in front of a whiteboard somewhere and working through this yourselves, and hitting all the question marks and figuring out exactly what this algorithm is about. Because just like everything else, but even more so in this case, you've absolutely got to understand the algorithm before you can code it. If you start writing code, or you start trying to type this stuff in and do something with it, you're heading down a really dangerous path. Because you're going to end up with code that you're going to be debugging without knowing what the algorithm is. And that's oftentimes where you end up with, when you do understand the algorithm, you can't get the code to work because you've got bits and pieces from other versions of the algorithm that you thought you understood. And it's just this big quagmire.
Would it be a smart idea to put the integer for max value, for the number that was saved, a global variable?
So with dynamic programming, our save array is usually going to be a global. right? So yeah, I would save those in like a global integer array. All right, so programming assignment 5, integer unlimited knapsack problem. So really important in this one that you have the names of all the people who are working in your group in comments in the beginning of your program. Okay, I would put it in every single file just to be safe. If someone's name's not there, they're not going to get credit for it. So make sure that's in there. And I'd only like one submission per group. Okay, if there's multiple submissions, I'll grade the first one I see alphabetically. So coordinate that amongst yourselves. And item 2 is just what I said in the beginning. Think about how you're going to break this into a group. All right, so details. Please call your program PA5. PA5 is run with a single argument, which is the capacity of the bag. So, and I was doing this in here. And I didn't call mine PA5, but I can get away with that. So I called it version 3, so I can put in the capacity of the bag, and it'll tell me what the maximum value is. So 11,200. Right, so if you put in something that's not an integer, it should tell you what you should do, which is type in the program name followed by the capacity. If you don't put in an argument at all, tell the user what they should do. Right, if you put in an illegal capacity, it should tell the user that your capacity should be between 1 and 1,024. So assumptions, maximum of 128 items in your inventory. This means you don't have to use malloc. You can make everything static. Your inventory is going to be a set of arrays. What do you have to store in your arrays? You have to store the weight of an item, the value of an item, and the name of an item. If there's a maximum of 128 items allowed, you can make these statically defined arrays. Integer weight bracket 128, value bracket 128, car star item bracket 128.
Would it be ideal to use a structure for this?
Be much better to use a structure for this. Right, so each item would have a field called weight, value, and name, or whatever, and then make an array of 128 of those structures. The name of the item is limited to 32 characters, so you don't have to use mallocs or car stars. You can make it a car bracket 33, right? 32 characters in an all terminator. There's no spaces in the name of the item, so you can scanf with a %s. %s normally stops when it gets to a space, but if your inventory includes a new car, it's going to be a underscore new underscore car exclamation mark, no spaces. So regular %s will ingest that nicely. And then the maximum bag capacity is 1,024, which means your save array that you're using to do the dynamic programming only has to hold 1,024 or 1,025 integers. So again, you don't have to malloc, and you don't have to make it a billion just in case, right? 1,024 is the maximum capacity. So you probably need 1,025 integers. We won't use element 0, but it doesn't hurt to have it. Okay, so there's simplifying assumptions that I usually put in to try to let you spend your energies on other pieces of the program. I want some error handling in here though, okay? So if there's no argument, if there's too many arguments, if it's an invalid argument, that should all generate error messages. Don't just ingest and run with a crazy number. And submit as a tar file, including a make file. All right, so the inventory itself comes from a file called knapsack.data. And it's assumed to be sitting in the directory that you're running the program from. And it's just 3 columns per line. So there's a weight, a value, and a name. And you can use this as a sample one if you want to test. And there's a copy of my executable on the Linux server under /temp pa5 sample. So you can take a knapsack file, you can run my code against it, see what it's giving you, and compare that to what your code is giving. Okay, so just extra checking. All right, and when you first process this file, right, look for errors. If the weight is not an integer, if the value is not an integer, you can say corrupt knapsack file, goodbye. All right, and then this is just a synopsis of the algorithm that we went through. So, suggestion, first thing your program does, open that knapsack.data file, read this information in, store it in your array or arrays. Okay, so that you're not continually doing file I/O. Open the file, read it in, save the information, close the file. And then call your maxval function with whatever argument you pass to the main program and print out the result. Okay, and so maxval works by returning the maximum of, and this is what we were writing out. So the value of item 0 plus maxval of x minus the weight of item 0, where x is the capacity. Value of item 1 plus maxval of your capacity diminished by the weight of item 1, and so on. And do this across all your items. Find the biggest value, return that. But only consider things where the weight of the item is not bigger than the capacity of the bag. If you try to call maxval with negatives, you will get wrong answers, even if you just return a 0. All right, is it making sense? Again, lots of parts and pieces here. If you work this out on a whiteboard or paper, right, and talk it over with other people so that you totally understand this paragraph, right, that's really the whole guts of the assignment right there, right? Find the maximum of those expressions. When you understand that totally, right, then start writing your code. And it's not complex in terms of data structures. There's no pointers other than maybe some strings. The recursion is, all right there. Reading in the knapsack file, parsing the command line arguments, that's all stuff you've been doing since 224, maybe since 121, right? So you may have to dust off those neurons, but it's stuff you've done before. But that's really the gist of the algorithm right there, just that highlighted part. Okay, so one more complicating detail, which is I also want to see the inventory of what you put in each bag, what you put in the bag, how much of each item. So when you run maxval, right, in addition to saying the maximum possible value is 99, go ahead and print out what your solution is. Item 1, put in one of those. Item 3, put in one of those. So this part is trickier. And I'm going to let you think about that yourselves, how you're going to get the inventory. But that's kind of an after the fact, right? Get the maximum value first. That's the most important part of this. But for full credit, you also want to show how many of each item you need, and we can talk about that a little more. But it's not going to make a lot of sense until you're more comfortable with the basic maxval algorithm. But basically, every time that you do one of these tentative calculations, right, this calculation is assuming that I'm adding item 0 to my bag. Well, if I somehow arrange for the maxval to tell me what the inventory of items is that gets me that maxval, if my maximum of all of these was C0, all I want to do is take the total count of item 0 and bump it up by 1. Because if C0 is the biggest of all of these, it means the max value for this capacity is the max value for this capacity plus one more item 0. So take the solution from this and increment the amount of item 0 by 1. if C1 was my biggest value, take the solution from this and increment the amount of item 1 by 1. If C3 is the biggest, take the solution from this max val, bump up the amount of item 3 by 1. So it's not complicated, but it's complex. Something like that. What you want to have happen is very simple, right? Just bump up the count of one item. But making that work in code is complex, because you need some way to pass back an inventory from this, which is either a pointer to a structure or something like that. Don't use globals here, right? Generally don't use globals anywhere with recursion. Generally don't use globals anywhere. But an exception that I'll allow will be for this save array for storing values, because that we really want every instance of maxval to hit the same array. And if you want to make your inventory global, I'll let you do that, just to minimize how much you're passing, because that never changes. That's just read only. So, questions? I suspect you'll have questions the more you work on this. Mm-hmm.
So what if we get the same max one, like for more than one situation we get the same max one?
Sure. So like if C2 and C3 are both the max? Yeah. You can pick either one.
Okay.
So the solution's not always unique. Right? So as long as you get a maximum value, you're good. And I think the only edge case in any of this is if your lightest item is heavier than the capacity of your bag, right?
Open space.
So if your bag holds 5 pounds, but your lightest item weighs 6 pounds, then there's no solution possible. Your max val is 0. And I think you have to code that up as an edge case. And what that's going to look like in your code is, you're doing some loop and you're only considering cases where the weight of the item is not bigger than the capacity. If none of these satisfy that, right, you're never going to come up with a possible solution to take the maximum of. But if you're doing this iteratively, if you start off by setting your maximum value to 0, and none of these are worthy of comparison, when you're done, your max value is 0. That's perfectly correct. So that's about 80,000 pieces of information I've given you, almost all of which are really important in the end. But you'll discover them on your own as you're going. All right, and throw in the dynamic programming piece. Without it, this thing will be a real dog. It'll just take forever to run, even on simple problems. And I'll put a knapsack.data file over there for you. All right, so you can use this knapsack.data, but you can make your own and work with that also. Good to go? All right. I will grade your PA5s sometime over the next few days, and I'll give you feedback in Canvas comments. And I will see you next time.
Yeah.